Alright, non-resident training course, November 1996. Steelworker Volume 1, Navedtra 14250. Distribution Statement A. Proof for public release. Distribution is unlimited. 1. Properties, use of metal. 2. Basic heat treatment. 3. Introduction welding. 4. Gas cutting. 5. Gas welding. 6. Soldering, brazing welding, wear facing. 7. Shield metal arc welding, wear facing. 8. Gas shield arc welding. Appendix Glossary 1. Appendix 2. Reference use to develop TRAMAN index. Alright, Chapter 1, Property Uses of the Metal. In the CB, the steel workers of the resident expert on the property use of metal we lay with the airfields, erect tower of the storage tanks, assemble pontoon causeways, construct buildings. We use our expertise to repair metal items, resurface warm machinery parts, and fabricate all types of metal objects. Competency with the task proficiently, one must possess a sound working knowledge of various metals and their properties. As we learn different properties, the characteristics we can select with the right type of metal, use the proper method to complete the job. Steel workers primarily work with iron and steel. However, we also must be familiar with the non-ferrous metals coming into use more and more each day. As a steel worker, we must be able to identify various metals and to associate with the individual properties with the proper application or use. Primary objective of this chapter is to present with a detailed explanation of some of the properties of the different metals, provide with the instruction and using simple tests establishing identity. Metal properties. There is no simple definition of metal, however, the chemical element having the metallic properties is classified as metal. Metallic properties are defined as luster, good thermal, electrical conductivity, the capability of being permanently shaped or deformed at a room temperature. Chemical elements lacking on the properties are classified as nonmetals. A few elements known as metalloids sometimes have like metal, other times like nonmetals. Some of the examples of metalloids are falls with carbon, phosphorus, silicon, and sulfur. Although steel workers seldom work with the pure metals, we must knowledgeable over the properties because of the alloys we work with a combination of pure metals. Some of the pure metals discussed in this chapter are the base metals in these alloys, the true iron, aluminum, magnesium. Other metals are discussed alloying elements present in small quantities, but important in their effect. Among these are chromium, molybdenum, titanium, and magnesium. An alloy is defined as a substance having the metallic properties that are composed of two or more elements. The elements for using alloying substances are usually metal and metalloids. Properties of the alloy differ from properties of the pure metal or metalloids that make up the alloy, but the difference is what it creates the usefulness of the alloys. By combining metals and metabloids, manufacturers can develop alloys that have the particular properties required for a given use. Table 1 is a list of various elements of their simple and composite metallic material. Aluminum, antimony, cadmium, carbon, chromium, cobalt, copper, iron, lead, magnesium, manganese, molybdenum, nickel, phosphorus, silicon, sulfur, tin, tungsten, vanadium, and zinc. Figure 1 shows from the left to the right the compression, the tension, shear, torsion, bending, and fatigue. Very rarely do we see steel workers work with elements of the pure state. Primarily work with the alloys, have the understanding of the characteristics of the elements. Alloys explained with the term physical, chemical, electrical, mechanical property. The physical property related with the color, density, weight, with the heat, conductivity. The chemical properties involved with the behavior of the metal when placed in the contact of the atmosphere, salt, water, or other substances. Electrical properties encompass the electrical conductivity, the resistance, magnetic properties of the metal. Mechanical properties relate to the loading, carrying ability, wear resistance, hardness, and elasticity. When selecting a stock for the job, your main concern is the mechanical properties of the metal, with the various properties of the alloys determined by the laboratory. Manufacture various societies interested in metallurgic development. The charts presenting the properties of the particular metal Alloy are available in commercial published reference books. These guitars are provided with the information, melting point, tensile strength, electrical conductivity, magnetic properties, other properties of the particular metal or alloy. Simple tests can be conducted to determine some of the properties of the metal. However, we are normally using the metal test only as an aid for identifying a piece of stock. Some of these methods of the testing is discussed later in this chapter. Mechanical properties: strength, hardness, toughness, elasticity, plasticity, brittleness, ductility, malleability are mechanical properties due to the measurement of how the metal behave under load. These properties are described in terms types of the force and stress of the metal withstand and how these are resisted. Common types of stress: compression, tension, shear, torsion, impact 1 and 2, or combination of these stresses such fatigue in figure 1-1. Compression stress: the development of the material when the force compresses, crushes the material. A column support for the overhead beam is in compression, and the internal stress for development when in the column are compression. Tensile: for tensile strength developed when material is subject to pulling a load. For example, when using a wire or rope to lift a load, when using as a guy for an anchor, and an antenna. Tensile strength is defined as a resistant longitudinal stress pull that can be measured in pounds per square inch with cross-section. Shearing stress occurs when external forces are applied along parallel lines in opposite directions. Shearing forces can separate material by sliding part into one direction and the rest to the opposite direction. Some materials are equally strong in compression, tension, and shear. However, the materials show the maximum marked difference. For example, the clear concrete has a maximum strength of 2,000 psi in compression, but only 400 psi in tension. Carbon steel has a maximum strength of 56,000 pounds in psi in tension and compression, but a maximum shear strength of only 42,000 pounds. Therefore, dealing with a max strength unit should always stay with the type of loading. A material is stressed repeatedly, usually fail with a point of considerably with a maximal strength with a tension, compression, or shear. For example, the thin steel rod can be broken by hand bending in the back and for several times in the same place. However, the same force is applied with the same motion and not bent back and forth. The rod cannot be broken. The tendency of the material to fail after repeated bending at the time this point is known as fatigue. Mechanical properties: toughness, copper, nickel, iron, magnesium, zinc, aluminum, lead, tin, cobalt, bismuth. Brittleness: white cast iron, gray cast iron, hardened steel, bismuth, magnesium, bronze, aluminum, brass, structural steel, zinc, monoclinical, tin, copper, iron. Ductility: gold, silver, platinum, iron, nickel, copper, aluminum, tungsten, zinc, tin, and lead. Malleability: gold, silver, aluminum, copper, tin, lead, zinc, iron. Corrosion resistant: gold, platinum, silver, mercury, copper, lead, tin, nickel, iron, zinc, magnesium, aluminum. Alright, strength is the property that enables the metal to resist the deformation under load. The ultimate strength of the maximum strength of the material can withstand. Tensile strength of the measurement of the resistance to being pulled apart when placed in tension load. Fatigue strength of the ability of the materials to resist various kinds of rapidly changing stress is expressed by the magnitude of the alternating stress for a specified number of cycles. Impact strength is the ability of the metal to resist suddenly applied loads measured in foot pounds of force. Hardness is the property of the material to resist permanently indentation because of the several of the methods of measuring hardness. Hardness of the material is always specified in the terms particular test that was used by the measure of the property. Rockwell, Vickers, or Brenell are some of the methods of the testing. One of the tests of Rockwell is most frequently used. The basic principle of the Rockwell test is that the hard material can penetrate a softer one. When we then measure the amount of the penetration compared to the scale of the ferrous metals, which usually harden with a non-ferrous metal with a diamond tip. The hardness is indicated by a Rockwell C number. Non-ferrous metal with a softer of the metal ball is the hardness is indicated by the Rockwell B number. To get an idea of the property of the hardness compared to lead and steel, lead can be scratched with a pointed wooden stick, but a steel cannot because it's harder than lead. Full explanation of various methods used to determine the hardness of the materials available with the commercial books or books located in the base of the library. Toughness. Toughness is the property that enables the material to withstand shock with deform with or rupturing. Toughness may be considered with a combination of strength and plasticity. Table 1-2 shows the order of some of the more common materials of toughness as well as the other properties. Elasticity. When a material load applied to it, load causes the material to deform. Elasticity, the ability of the material to return the original shape after the load is removed. Theoretically, elastic limit of the material is limited, the material can be loaded and still recover the original shape after the load is removed. Plasticity is the ability of the material to deform permanently without breaking or rupturing. To the property with the opposite of strength, by careful alloying of the metal. The combination of plasticity and strength is used to manufacture large structural members. For example, should a member of the bridge structure become overloaded, plasticity allows the overloaded member to flow, allowing the distribution of the load to other parts of the bridge structure. Brittleness. Brittleness is the opposite of the property plasticity of the brittle metal, with the one that breaks and shatters before it deforms. White cast iron, glass, with a good example of brittle material. Generally, brittle metals are high in compressive strength but are low in tensile strength. As an example, you can now choose the cast iron for fabrication support beams in a bridge. Ductibility and malleability. Ductibility is the property that enables the material to stretch, bend, and twist, or without cracking or breaking. This property makes it possible for the material to be drawn out into a thin wire in compression. Malleability is the property that enables the material to deform by compression forces without developing effects. The malleability material is one of the stamped, hammered, forged, compressed, or rolled into thin sheets. Corrosion resistance. Corrosion resistance, although not mechanical property, important with the discussion material, but the corrosion resistance of the property of metal gives the ability to withstand the attacks of the atmospheric, chemical, electrochemical conditions. Corrosion, sometimes called oxidation, illustrated by corrosting an eye of iron. Table 1-2 lists the 4 mechanical properties of the corrosion-resistant various metals with the alloys. First, metal and alloy. Each column exhibits the last character of the property of the last metal of the alloy, and each column exhibits the least. And the column labeled the toughness. Note that the iron is not the toughest as copper or nickel. However, it is tougher than magnesium, zinc, and aluminum. In the column ductility, iron exhibits a reasonable amount of ductility. However, in columns labeled malleability and brittleness, it is last. Alright, metal type of the metal. Steelworkers work with divided with the 2 general classification: ferrous, non-ferrous. Ferrous metals are composed primarily of the iron and iron alloys. Non-ferrous metals are composed primarily of some element or elements other than iron. Non-ferrous metals and alloys sometimes contain a small amount of iron and alloying element or as impurity. Ferrous metals include all forms of iron and steel of the alloys. For example, the iron rope, the iron cast iron, carbon steel of the alloy, steel of the tool, steel. Ferrous metals are iron-based alloys with small percentage of the carbon. Other elements are added to achieve the desired property. Normally, ferrous metals are magnetic. Non-ferrous metals are not magnetic. Pure iron exhibits outside of the laboratory. Iron produced for producing iron or to pig iron through the use of a blast furnace. From pig iron, many of the other types of iron and steel will produce additional dilution, carbon, and alloys. The following paragraph discusses the different types of iron and steel that can be made from pig iron or pig iron. It is compressed about 93% iron and from 3 to 5% carbon. Various amounts of the other elements. Pig iron is comparatively weak and brittle. Therefore, it's limited to use approximately 90% and produces refined to produce steel. Cast iron pipes, sometimes some fittings and valves are manufactured from pig iron. Wrought iron is made from pig iron with some slack mixed in during manufacture. As a pure iron, presence of slacks enables wrought iron and to resist corrosion oxidation. The chemical analysis: wrought iron, mild steel are just about the same. The difference comes from the property of control during the manufacturing process. The iron can be gas, arc, welded, machine plated, and easily formed. However, it has a low hardness and a low fatigue strength. Capability, or cast iron. Cast iron is any iron containing greater than 2% carbon alloy. Cast iron has a high compressive strength. Good wear and resistance, however, is lacks ductility, malleability, impact strength, and alloying it with nickel, chromium, molybdenum, silicon, or vanadium improves toughness, tensile strength, and hardness. Malleable cast iron is produced through a prolonged annealing process. Ingot iron. Ingot iron is commercially pure with an iron of 99.85% iron. The easily formed and processed, good ductility, corrosion resistant. Chemical analysis: property of the iron. Lowest carbon steel, particularly the same. Lowest carbon steel known as dead soft, has about 600 of a percent more carbon than ingot iron. Iron containing iron that carbon content is considered an impurity in steel, considered with the alloying element. Primary use of the ingot iron is for galvanized and able to sheet. Steel, other different metals of the we use in our trade. Steel is by far the most important. When steel was developed, it revolutionized for the American iron industry. When it came, skyscrapers stronger and longer bridges, railroad tracks didn't collapse. Steel manufactured for the pig iron, decreasing the amount of the carbon and other impurities, adding specific amounts of alloying elements. Do not use steel. Confuse steel with a huge general class of the iron. Cast iron greater than 2% carbon and pure iron less than 1,500% carbon. In steel manufacturing, control the amounts for the alloying elements added during the molten stage produce the desired composition. Composition of steel determine the application specification that were developed by the following: American Society of Testing Materials, American Society of Mechanical Engineers, and the Society of Automotive Engineers, American Iron and Steel Institute. Carbon steel is a term applied for the broad range of steel that falls with commercially pure ingot iron and cast irons. This range of carbon steel may be classified in four groups: low carbon steel, 500s to 3/10 of carbon; medium carbon steel, 3/10 to 4500s of the carbon; high carbon, 4500s to 7500s carbon; very high carbon steel, 7500s to 1.7 percent carbon. Low carbon steel. Steel is classified with a tough, ductile, easily manufactured form, welded, but does not respond to any of the form of the heat, the treating, except the case of hardening. Medium carbon steel, but the steels are strong, hard, and they cannot be welded and worked as easily with the low carbon steel, but they use the crane, hooks, axles, shafts, set screws, or so on. High carbon steel, very high carbon steel. Steel in the classes of the respond well with the heat treatment can be welded. When welded, special electrodes must be used along with the preheating, stress relieving procedure to prevent cracks in the weld of the area. The steels are used with the dies, cutting tools, mill tools, railroad cars, wheels, chisels, knives, and so on. Low alloy, high strength, temperature structural steel. A special low carbon steel that contains specific small amounts of the alloying elements, quench temperature for the gate with a yield strength greater than 50,000 psi, tensile strength of 70,000 to 120,000 psi. Structural members made with the high strength steels may have smaller cross sectional area, but the common structural steels are still have equally or greater strength. Additionally, these steels are normally more corrosion and abrasion resistant. High strength steels are covered by ASTM specification. Note this type of steel is much tougher than low carbon steel. The shearing machines of this type of the steel must have twice the capacity required for low carbon steel. Stainless steel. The type of the steel classification: American Iron Steel Institute, with the two general series named the 200, 300 series, and the 400 series. Each series includes several types of steel with different characteristics. 200, 300 series stainless steel is known as austenitic. The type of steel is very tough with the ductile as well with the welded condition, therefore is ideal for the welding, requires no annealing under normal atmospheric conditions. Most well-known types of steel in this series are the 302 and the 304, commonly called 18-8 because it is composed of 18% chromium and 8% nickel. Chromium nickel steels are most widely used but normally non-magnetic. The 400 series of steel is subdivided according into crystalline structures, two general groups. One group known as the ferritic chromium and the other group marcentinic chromium. Ferritic chromium is the type of steel that contains 12% to 27% chromium, or 8/100 to 20% carbon. This alloy straightened chromium grades of stainless steel since they contain no nickel. There are no hardenability with the heat treatment normally used in the annealed soft condition. Ferritic steels are magnetic and frequently used as decorative trim and equipment subject to the high pressure and temperatures. Marcentinic chromium. Steel is magnetic and already hardened by heat treatment. They contain 12% to 18% chromium, 1/1500 to 1.2% carbon, and 2.5% nickel. The group is used wherever the high strength corrosion resistance ductility are required. Alloying steels. Steels are different with the properties prominently with the presence of some alloying elements other than the carbon allowed, called alloys or alloy steels. Note, however, the alloy steels always contain traces of the other elements. Among the more common alloying elements are nickel, chromium, vanadium, silicon, tungsten. One or more of these elements may be added to the steel during the manufacturing process to produce the desired characteristics. Alloying steel may be produced in structural sections, sheet plates, Bars for series is rolled with the condition material and better physical properties with attained with this. These steels are possible. High rolled carbon steels. These alloys are even in structure with the strength of the material, especially important. Bridge maneuvers, railroad cars, dump bodies, dozer blades, crane booms that are made with the alloying steel. Some of the common alloying steels are briefly described in the next paragraph below. Nickel steel. Steels containing 3.5% nickel to 5% nickel. The nickel increases the strength and toughness of these steels. Nickel steel contains more than 5% nickel. Has been increased resistance to the corrosion and scale. The nickel steel is used in the manufacturing aircraft parts and such propellers, airframe support members. Chromium steels. These steels are chromium added to improve the hardenability, wear resistance, strength. The steel contains about 200 to 75 hundredths percent chromium and 45 hundredths of a percent of carbon or more. Some of these steels are so highly resistant to wear that they are used for races and balls, anti-friction bearings. Chromium steels highly resistant to corrosion and to scale. Chromium vanadium steel. The steel has a maximum amount of strength, less amount of weight. Steel of the type contains from 1500 to 2500% vanadium, 6/10 of the 1.5 chromium, and 1/10 to 6/10 of a percent of carbon. Common use of the crankshaft, gears, axles, other items require high strength. The steel is also used with the manufacture of high quality, high end tools and such wrenches and sockets. Tungsten steel, the special alloy that has the property of the red hardness. This ability is to continue to cut after it becomes red hot. A good grade of steel contains from 13% to 19% tungsten, 1 to 2% vanadium, 3 to 5% chromium, 6/10 to 8% tenths of the percent carbon. Because the alloy is expensive to produce, usually largely restricted to manufacture drill, lathe tools, milling cutters, similar cutting tools. Molybdenum, this often used the alloying agent. Steel combination chromium and nickel. The molybdenum adds toughness to the steel. It can be used in place with tungsten to make it cheaper grades with high speed steel in carbon molybdenum high pressure tubing. Magnesium steel. The amount of magnesium depends on the property desired. The finish of the product with small amounts of the magnesium produce strong free machining steel. Large amounts between 2% to 10% produce somewhat brittle steel, while still larger amounts 11% to 14% produce steel that is tough and very resistant to wear after proper heat treatment. Non-ferrous materials. Non-ferrous metals contain either no iron or only insignificant amount used in alloys. Some of the other more common non-ferrous metals steel workers work within are fouls, copper, brass, bronze, copper, nickel alloys, lead, zinc, tin, aluminum, beryllium. Note these metals are not metallic. Copper. The metal is the alloy that maintains many desirable properties. Among the commercial metals is one of the most popular. Copper is ductile, malleable, hard, tough, strong, wear resistant, machinable, weldable, corrosion resistant. Also has a high strength, high tensile strength, fatigue strength, thermal electrical conductivity. Copper is one of the easier metals to work with and be careful with because it easily becomes hardened. However, this condition can be remedied by heating it to cherry red and letting it cool. The process called annealing restores the softening cooling to a softened condition. Annealing and softening are one of only heat treating procedure that apply to copper. Seams in copper are joined by riveting, silver brazing, bronzing, brazing, soft soldered gas welding, or electrical arc welding. Copper is frequently used to give the protective coating to sheets, rods, to make ball flows, containers, and soldering coppers. True brass. The alloy copper and zinc. Additional elements such as aluminum, lead, tin, iron, magnesium, phosphorus are added to give the alloy specific properties. Natively rolled brass, tin, Tobin bronze contains about 60% copper, 39% zinc, and 75 hundredths of a percent of the tin. The brass is highly corrosion resistant, particularly with the impurity of free. Alright, brass sheets and strips available in several grades. Soft, 1/4 hard, 1/2 hard, full hard. Spring grades. Hardness is graded with the process cold ruling. All grades brass are softened by annealing at a temperature of 550 degrees Fahrenheit to 600 degrees Fahrenheit, then allowing it to cool by itself without quenching it, overheating, and it can destroy the zinc to alloy. Bronze. Bronze is a combination of 84% copper with 16% tin, where the best metal available with the steel making techniques were developed. Many complex bronze alloys contain such elements as zinc, lead, iron, aluminum, silicone, phosphorus, and are now available Today, the name bronze is applied to any copper-based alloy that looks like bronze. In many cases, there are no real distinction between composition bronze and brass. Copper-nickel alloy. Nickel is used for the alloys to make for the stronger, tougher, resistant wear. Corrosion because of the high resistant corrosion. Copper-nickel alloys contain 70% copper, 30% nickel, 90% copper, 10% nickel. Are used in saltwater piping systems. Some small storage tanks and hot water reservoirs are constructed of copper-nickel alloy. This is available to sheet form. Copper-nickel alloy should be joined in metal arc weld by brazing. Lead. Heavy metal that weighs about 710 pounds per cubic foot. In spite of the weight, lead is soft, malleable, and available in pig in sheet form. In sheet form, it is rolled upon the rod user and roll until it's unrolled, cutting off the desired amount. The surface of lead is grayish in color. However, after scratching and scraping it, you can see if the actual color of the metal is white because the soft lead is usually made backing material when punching holes with a hole puncher when forming shapes by hammering copper sheets. Sheet lead is also used to line sinks, protect bench tops when a large amount of the acid is used. Leaded line pipes are used as a system to carry out corrosive chemicals. Frequently, lead is used in the alloy form to increase the low tensile strength of the alloying. The tin lead produces a soft solder. When adding to the metal of the alloys, lead improves the machinability. Caution: when working with lead, you must take the other precautions because of the dust and fumes and vapors from it that are highly poisonous. Zinc. You often see zinc and iron or steel in the form of a protective coating called galvanizing. Zinc is also used in soldering, fluxes, die casting as an alloy and making brass and bronze. Tin has many important uses. Alloys. It can be alloyed with lead, produce sulfur solders with the copper, and bronze produce bronze. Tin-based alloys have high tensile strength, high resistant corrosion, low fatigue strength, and a compressive strength that accommodates light or medium loads. Tin, and like lead, has a good resistance to corrosion and have the added advantage of not being poisonous. However, when subject to extreme low temperatures, it has a tendency to decompose. Aluminum. This metal is easy to work with and is good appearance. Aluminum is lightweight and high strength per unit weight. The disadvantage is that the tensile strength is only 1/3 of that of iron, 1/5 of the annealed mild steel. Aluminum alloys usually contain at least 90% aluminum. In addition, silicon, magnesium, copper, nickel, magnesium can raise the strength of the alloy to the metal. Steel. Aluminum in pure state is a softer and stronger affinity for gases. The use of the allowing elements used to overcome these disadvantages. However, the alloys, unlike with the pure aluminum, corrodes unless given a protective coating. Threaded parts made by aluminum alloy should be coated with the anti-seize compound to prevent sticking caused by corrosion. Alright, then we have another chart. Metals: white cast iron, color unused, broken surface, dull gray, silvery white structure, crystalline, silver white color, freshly filled surface. Gray cast iron, dull gray, dark gray, crystalline, light silver gray. Malleable iron, dull gray, dark gray, finely crystalline, light silver gray. Wrought iron, light gray, bright gray, light silver gray. Low carbon steel, dark gray, brighter silver gray. High carbon steel, dark gray, light gray, brighter silver gray. Stainless steel, dark gray, medium gray, brighter silver gray. Copper, reddish brown to green, bright red, bright copper color. Bright brass bronze, reddish yellow, yellow green or brown, red to yellow, reddish to yellowish white. Aluminum, light gray, white, finely crystalline, and white. Mono metal, dark gray, light gray. Nickel, dark gray, off-white, bright silver white, and lead, white to gray, light gray, crystalline, and white. Alright, beryllium. One of the first stronger structural aluminum alloy developed is called beryllium. It developed a variety of different raw iron aluminum alloys. Number system was adopted. Digits indicate the measuring alloying element. The cold work heat treating condition of the metal. The alloy, originally called the beryllium, is known classified in the metals working industry as 2017T. The letters T indicates the metal has heat treated. Alkali. The protective coating consists of a thin sheet of the pure aluminum rolled surface with aluminum alloy during manufacturing. Zinc chromate is protective covering that can be applied to aluminum surfaces. Needed zinc chromate is also used with the primer steel surface and protective coating. Mono is an alloy which the nickel is a major element. It contains 64% and 68% nickel, about 30% copper, and small percentage iron, magnesium, and cobalt. Mono is hard, strength than either the nickel, or is stronger than either is harder and stronger than nickel or copper, and highly conductive. Ductility has high ductility. Resembles stainless steel in appearance and has many qualities. Strength combined with a high resistance to corrosion make mono an acceptable substitute for steel in systems where corrosion resistance is primary concern. Nuts, bolts, screws, various fittings are made of mono. This alloy can be worked in cold and can be forged and welded. If worked at temperatures range between 1200 and 1600 degrees Fahrenheit because of hot, short, or brittle. Hot, short, or brittle. K mono, the specific type of alloy developed by a greater strength, hardness, and than mono in the strength it is comparable to heat-treated K mono as used with the instrument parts for the more resistant corrosion. Alright, Incanal. The high nickel alloy is often used with the exhaust system of the aircraft and engines. Incanal composed of 78.5% nickel, 14% chromium, 6 to 0.5% iron, 1% other elements. It offers good resistance to corrosion and retains strength at high operating temperature. Metal identification. Many methods of identifying a piece of metal. Identification necessary selecting the metal with the fabrication, determining weldability. Some of the common methods used in the field of identification: surface appearance, spark test, chip test, use of magnets. Surface appearance. Sometimes it's possible to identify materials by their surface appearance. Table of 1-3 to identify the surface colors. Some of the more common metals. Referring to the table, you can see the outside appearance of the metal helps identify and classify material with newly fractured and freshly filled surfaces with other additional clues. Surface examination does not always provide enough information identification, but should give us enough information to place the metal into a class. The color of the metal is distinct with the marks. It allows, because of the manufacturing help, determine the identify with the metal. The cast iron, malleable iron usually show the evidence of sand mold. Low carbon steel also often shows with the forging marks. High carbon steel shows either a forging or rolling marks. Feeling or surface may be provided with another clue. Stainless steel is slightly rougher than the unfurnished state. Surface wrought iron with the copper, brass, bronze, nickel, mono, and smooth lead. Also in smooth volatility appearance. When surface appearance of metal does not give enough information to allow for the positive identification, other identification tests may become necessary. Some of these tests are complicated and require equipment we do not usually have. However, the other tests are fairly simple and reliable when done by a skilled person. 3 of these tests also are the spark test, chip test, and magnetic test. Our figure 1-2 shows the terms of the sparking test. Shows a stream, a shaft, a fork. Your springs, your dashes, and your appendages, your bud break arrows. The spark test is made with holding a sample of the material against a abrasive wheel with a visual inspection spark stream. Experienced metal worker can identify the metal's considerably accuracy. With the test, the fast, economic, convenient, with the easily accomplished. There is no requirement for the special equipment we can use to identifying with the metal salvage from scrap. Identification of scrap is particularly important when selecting material for the cast iron cast steel heat treatment. When holding a piece of the iron steel within contact with a high-speed abrasive wheel, small particles of the metal are torn loose so rapidly they become red hot. As the glowing bits of the metal leave the wheel, they follow the path of the trajectory called the carrier line. This carrier line is easily followed with the eye, especially when observed when against a dark background. Spark often given off or lack of sparks in the identification of the metal. Length of the spark with the stream, the color, form, sparks, and features should be looked at in Figure 1-2, illustrating the term used referring to various basic spark forms produced in the spark test. Seals have some carbon content differing element. The difficulty to identify with the elements effect of the carrier lines of the burst, and it forms a characteristic burst and spark picture effect. Alloying element may be slower, accelerate. The carbon sparks made with the carrier line lighter or darker in color. Molybdenum, for example, appears as attached. Orange color superheaded on the end of the carrier line. Nickel appears as suppressed, effective with the carbon burst. However, the nickel spark can be identified. Tiny blocks of brilliant white light. Silicone suppressed with the carbon burst even more than nickel. When silicone is present with the carrier line, it usually ends abruptly with a white flashlight. The spark testing may be done with either a portable stationary grinder. It can in either case the speed of the outer rim of the wheel should not be less than 4,500 feet per minute. Abrasive wheels should be rather coarse and very hard and kept clean to produce a true spark. You conduct a spark test. The abrasive wheel hold the piece of the metal with the wheel position and allow the spark stream to cross your line of vision by trial and error. You soon discover the pressure is needed to get the stream of the proper length with the reducing speed with the grinder, except for the pressure, increase the temperature of the spark stream. This in turn increases the temperature of the burst, giving the appearance of the high carbon content actually is present. When making the test, watch a point of about 1/3 of the distance of the tail end of the spark stream. Watch only the sparks that cross your line of vision. Try to form a mental image of the individual spark. Fix the spark image in your mind, then examine the whole spark picture. While on the subject abrasive wheel, with a good idea to discuss some of the safety precautions associated with the tool. Never use an abrasive wheel that is cracked or out of balance because of the vibration can cause the wheel to shatter. The abrasive wheel shatters. It can be disastrous or personal standing line wheel. Always check the wheel with obscure mounting cracks before putting it into use. Install the new wheel with a grinder. Be sure with the correct side. Remember, increase the wheel radius, the peripheral speed rim increase, and even though the driving motor of the RPM remains same. Thus, it should use an oversized wheel with a distinct danger for the preferable speed. The consequential centrifugal force can become great as the wheel may fly apart. Use the wheels of the design specific RPM guards are placed on the grinder's protection in case the wheels should shatter. Never use a grinder with the guards without having to remove the turning of the grinder. You stand one to one side. It places you out of line with the wheel in case the wheels should burst. Never overload a grinder. Put sideways pressure against the wheel unless it's expressly built to withstand such a use. Always use appropriate safety galv fixture will then leave the grinder and ensure the tool rest of the device that helps the operator hold the work is adjusted with the minimum clearance of the wheel. Move the work across the entire face of the wheel to eliminate groove and minimize wheel duressing. Of doing this, it prolongs the life of the wheel. Keep your fingers clear of the abrasive surface. Do not allow rags, clothing to become entangled within the wheel. Do not wear gloves while using an abrasive wheel. Never hold metals with the tongs while grinding. Never grind non-ferrous metals on a wheel intended for the ferrous metals because of the misuse of the clogs. Pores of the abrasive material will build up the metal and may cover to become unbalanced and fly apart. Grinding wheels. Grinding wheels require the frequent recondition dressing even to describe the process of cleaning the peripheral with the cleaning brakes will always dull abrasive grain smooth with the surface of removing all the grooves in the wheel dresser shown in figure 1.3. Use for the dress grinding wheels on the bench and pedestal grinders. For more information on grinding wheels, you should consult Chapter 5 of the NAVDTRA 185B2 tools and their use. Referring to now to figure 1.4, notice low carbon steel view A. The spark stream is about 70 inches long volume and a moderately large high carbon steel view B. Stream is shorter, about 55 inches view or long volume larger. Few sparks over the may occur with any place the low carbon steel are forward. Figure 1.3 shows using the grinder, wheel dresser, safety hood, wheel dresser. Alright, spark A is sparks produced from low carbon steel, spark produced by high carbon steel B, and sparks produced with gray cast iron. D, sparks produced with mono and nickel, sparks produced with stainless steel, sparks produced for wrought iron. And then we have table 1.4 metal identification chip test. White cast iron chips and small brittle fragments. Chip surface not smooth. Gray cast iron chips about 1/8 of an inch in length. Metal not easily chipped, therefore chips break off to prevent smooth cut. Malleable iron chips are vary from 1/4 to 3/8 of an inch in length. Larger chips from cast iron metal is tough with a harder grip. Wrought iron chips are smooth edged. Metals are easily cut or chipped to the chip that can be made with a continuous strip. Low carbon cast steel chips have smooth edged. Metal is easily cut or chipped, and chip can be taken off with a continuous strip. High carbon steel chips shown with a high fine grade structure, easily chipped with lighter color bleed chips. Low carbon steel metal is hard and can be chipped in a continuous strip. Copper chips are smooth with soft tooth edges where cut metal is easily cut in continuous strips. Brass and bronze chips are smooth with sawtooth edges. Metals are easily cut, and chips are more brittle with the chips of copper. Continuous strips is not easily cut. Aluminum and aluminum alloy chips are smooth, sawtooth edges. Chips can be such continuous strip. Mono chips are smooth. Continuous strip can be cut. Metal chips are easily. Nickel chips have a smooth edge. Continuous strip can be cut. Metal chips easily. Lead chips are any shape that may be obtained and become because the metal is so soft that it can be cut with a knife. Alright, in high carbon steel, there are small repeating both metals produced with a spark stream of the white in color. Gray cast iron VUC produces stream sparks with about 25 inches in length with a sparkler, or small repeating volume and rather small. Part of the stream near the wheel is red with the outer portion straw colored. Model nickel VD form almost identical spark stream, and the sparks are small in volume and orange in color. Sparks from wave streaks with no sparklers because of the similarity of spark picture. These metals must be distinguished from either of some of the other method. Stainless steel View E produces a spark stream about 50 inches in length, moderate volume, with a few sparklers. Sparklers are forked streams next to the wheel shawl colored at the end of the white. Wrought iron spark View F produces a spark stream about 65 inches in length. The stream has a large volume with a few sparks. Sparks appear near the end of the stream and are forked. The streams next to the wheel and straw colored. The outer end of the stream is brighter red. One way to become a proficient spark testing ferrous materials is gathering assortment of samples known as metal and test them. Making all the samples about the same size, shape, and identified if they're not revealed simply by size and shape. Normally, each sample will prepare a list of names corresponding with the number within without looking at the number of the samples of spark tests and one sample at a time. Calling out its name to someone assigned to check it against the name of the numbers on the other list. Repeating the process gives some of the experience you need to become a proficient in identifying individual samples. Alright, the chip test. Another simple test. You can identify an unknown piece of the material. Chip test. Chip test made with removing a small amount of material with a test piece. Sharp, cold, chisel. Material removed varies from small broken fragments. Thin strip chips may be the small, sharp edge. Maybe coarse grain, fine grains, may have saw-like edges. Size of chips important to identify with the material or the metal. The ease of which shipping can be accomplished should also be considered. The information given in Table 1-4 can help you identify various metals in chip tests. Or the magnet test, use the magnet and other methods use the aid of the general identification of metals. Remember that ferrous metals, being iron-based alloys, normally are magnetic. Non-ferrous metals are non-magnetic, and this test is not 100% accurate because some stainless steels are non-magnetic. In this instance, there is no substitute for experience. Chapter 2, Basic Heat Treatment.